All right, welcome to the Unit 6 notes. This will be the first video for Unit 6. We'll cover all 13 topics for Unit 6 in these videos. Some of the topics are very short, so they might be included with another topic in a video, so there might not be exactly 13 videos. We will go through renewable and non-renewable resources, global energy consumption, fuel types and uses, distribution of natural energy resources, fossil fuels, nuclear power, energy from biomass, solar energy, hydroelectric power, geothermal energy, hydrogen fuel cell, wind energy, and energy conservation. So you'll notice that 6.5 through 6.12 are all individual types of energies that we'll look at in depth. To get started, this will be 6.1, renewable and non-renewable resources. This is a very short introduction video. In class, we watched this TED Ed video, so make sure if you get a chance, if you did not watch it in class with us, or you would like to watch it again, it is posted at that link right there. You can either write that down and put it into your browser, or you can find this PowerPoint on our Microsoft Teams and copy and paste that link as well. So, non-renewable resources, the essential point of a non-renewable resource is that in a human time scale, it does not become replenished. So, if we use it, it is no longer usable. So, like oil, coal, natural gas, and nuclear, those are the big ones. They are used up and then will not replenish themselves again. Once we use, say, all of our oil reserves, there will not be any more oil added for us to get. Obviously, over millions of years, these resources may replenish themselves, but not on a human time scale. Now, that's opposed to renewable resources, which actually will be replenished naturally, typically at the same or near the same rate that we consume the energy source. Solar, biomass, hydropower, geothermal, and wind would be considered the big ones for this. We'll look at all of these sources in depth. Just remember that non-renewable are not replenished in a human time scale, whereas renewable can be. So that'll bring us to 6.2, which is all about global energy consumption, looking at how we use the energy that we have. Now, when we get to the energy unit, one of the big things is that we are looking at a little bit of math. So it's important that you know these units. The basic energy unit is a joule. A gigajoule is a billion joules, which is the amount of energy in 30 liters of gas. An exajoule is a billion gigajoules. And then a quad, which is a term that we actually only really use in the United States, is just a quadrillion British thermal units, a BTU, which is equal to 1.055 exajoules. So remember, an exajoule is a billion gigajoules, a gigajoule a billion joules, so you can actually find a quad we could convert all the way down into a joule, or how many joules there are. So we're going to look at this with a little bit of dimensional analysis. This is the easiest way to do these problems, just because all dimensional analysis does is looks at the units so that we can cancel those units out to get to the units that we want. So this problem asks, in 2011, the total world energy consumption was approximately 520 quads per year. And what we're wanting to know is how many gigajoules that is per person every month. So the units that we want to end with are gigajoules per person per month. And so the easiest way to kind of start this problem, you could start with 521 quads per year. That would be completely fine. You could start with what you're given and try to figure out how to get to where you're going. The other thing you can do is try to get the units that you want in your answer to just start being in the problem. So, for instance, in this problem, we want gigajoules per person per month. So the very first thing that we're going to do is try to get gigajoules on the top, because we know that we need gigajoules on the top when we get to our answer. We use that gigajoules per exajoules because I know from that last slide that we can get quads to exajoules. If you recall back on the slide previously, one quad was 1.055 exajoules. So if I can get my gigajoules to be exajoules, or what exajoules are, now we can cancel out our exajoules knowing that it's 1.055 exajoules per quad. Just by doing that, the reason I wanted to do that is because now I can use this quad and have it cancel out with the quads in our given problem. So we had exajoules canceled out here, and that was because they are on opposite sides. One's on top, one's on the bottom, so they'll cancel out. Gigajoules does not cancel out with quads because they're not the same unit. So right now we have gigajoules per quad. We want to get rid of quads because at the end we want person and month on the bottom. So we're going to look at how many quads there are maybe per person. But before we do that, we have to figure out how many quads there are per year. There's 521 quads in 1 year. That was one thing that was given to us. So considering that, we're going to now say we have gigajoules per year. We've canceled out our quads, we've canceled out exajoules, we're left with gigajoules per year. We want gigajoules eventually per month, so we can actually get rid of years and get ourselves into months right now. We know that 1 year is 12 months. So at this point here, doing these 4 conversions, we were able to get gigajoules on top, which is what we need, and months on bottom, which is also what we need. The only other thing we need here is to get persons on bottom. So we know that there are approximately 7 billion people. So 7 billion people in a year, roughly. That gets us people on the bottom. And now we are able to say we have gigajoules times years divided by months and people per month. The reason that this year ends up canceling out is because we're doing this for just 1 year. So this unit really doesn't even need to be there, but that cancels out based on the fact that we're only looking at 1 year of time. So in reality, we would have 1 year total that we're looking at. If we do the math on this, 10 to the 9th times 1.055 times 521 times 1 times 1, you'll get a certain number. On the bottom, we have 1 times 1 times 1 times 12 times 7 billion. And then you just take your top, you divide it by your bottom, and you'll end up with 6.5435 gigajoules per person per month. Now you can assume that this number, because this is the global energy average, this is probably a low estimate if we were looking for people in developed countries, and a high average or high estimate for people living in developing countries. So if we look at the energy use per capita, you can get that feel. The United States uses far more energy per capita than any other country, followed closely by Russia. You would think China, they have a huge population, they use a lot of energy. While China does in fact use a lot of energy, their per capita is very low, and the reason their per capita is pretty low is because they don't use as many per person. They have many people. They don't use nearly as much energy per person as other countries like Italy, UK, Japan, Germany, France, Russia, and of course the United States. So we talked about developed and developing countries, specifically when we were looking at that problem where we would assume that estimate was probably high for one and low for the other. Commercial energy sources, typically we're going to see these in developed countries. So we're looking at these sources that are bought and sold that we can get. Oil, coal, natural gas. You don't have an oil plant in your backyard that you're burning oil and, producing your electricity. On the other side, we have subsistence energy sources. These are sources that are gathered by people and used by people. So that would be like wood or straw, sticks, animal dung, mostly biomass realistically, because these are things that you have to gather, or the people gather, collect, and then use directly for their own energy sources. So as industrialization increases, we know that energy use will increase. And because energy use increases, we have to change the sources of energy that we have. So we can look at this graph. This is the United States history of energy consumption since the beginning of the United States. And you can actually see here that wood was primarily the main energy source until about the mid 1800s, with the introduction of coal. Right after coal was introduced, only a few years later, petroleum began to be discovered, used very small amounts until the 1900s, and of course hydroelectric in the late 1800s beginning to be used, still always at a fairly small number. We can actually see here in the late 1800s natural gas being discovered and used, but for the most part we didn't see a spike of natural gas until later, and now we actually see petroleum and coal starting to fall away as our primary source, and natural gas beginning to rise. And we'll talk about why right on this page. So, the predominant energy source until 1875 was wood. If you remember, for the most part in the United States, we were using wood energy. At that point, we switched over with the discovery of coal, so coal became the main source. Now, what source didn't begin until 1950? Well, that would be nuclear. And the reason for that, of course, was nuclear research and nuclear understanding of nuclear power was not really understood. In the 1970s, there was a dramatic dip in oil. This was actually considered the oil crisis of the 70s, where it was believed that the oil resources, the oil reserves, were starting to become depleted, which saw a spike in oil prices. And many gas stations, if you have parents that were around in the 1970s, or if you have maybe grandparents, they would probably remember waiting in long, long lines to get gasoline because many of the gas stations were out of gas. And so you had to wait in long lines just to be able to fill up your car. So today, the top three sources are oil, natural gas, and coal, non-renewable resources, of course. Since 2000, that's where we've started to see the increase in natural gas, and the reason why is because of the availability with fracking. Because of fracking, which we'll talk about as we get into our natural gas subunit, fracking has allowed us to easily retrieve natural gas much cheaper than before, and because of that, natural gas is becoming predominantly used, and there's a lot of natural gas available in the United States, which makes us a little more energy independent. So this is just a graph to show you the energy consumption by energy source in the United States. This is 2014 versus 2017, and you can see in 2014 petroleum was 35, 2017 it actually went up. The number of quads was actually lowered from 98.3 to 97.7. Natural gas began to be used more, but coal is starting to see a decrease, and you can actually see 4% are dropping down. Now, nuclear power has gone up by 1%. Renewable energy has gone up by 1%. You can actually see that in the renewable energy sources, we're actually seeing more wind energy and slightly more solar energy. But for the most part, the other sources were using less wood and about the same amount of hydroelectric power. Now, this should not come as a huge shock to you. Energy, the use of energy varies very much depending on the region and the season. So in the Midwest and the Southeast, coal is used for electricity. Because of its ease of access. There's a lot of coal mines in the Midwest and the Southeast. In the West and the Northeast, on the other hand, nuclear, natural gas, and hydroelectric are very commonly used. Now, in highly populated areas, typically you're going to see less coal usage, and the reason for that is because when you have a high population, you want to decrease the air pollution. The North, of course, uses more energy in winter. Hopefully you know why. It's because we have to heat our homes in the cold, cold winter. And the South is going to use more energy in the summer, and the reason for that, of course, is because it's very hot in the summer and they need air conditioning. So this just shows you a breakdown of energy consumption in the United States. Buildings take up 39%. Of that 39%, you break that into 21% and 18% if you just want to look at residential versus commercial. Industrial is 33% and transportation is 28%. So just getting things moved around the country is a huge, almost a third of our energy use. Now, you might ask, well, why don't we just use gas? Why do we use gas and diesel instead of coal and firewood, since, say, firewood, for instance, is renewable? And the big reason is because you would need a lot more wood or coal to power your vehicle than it would take with gasoline or diesel. There's a lot more energy to mass ratio. You get more energy versus the amount of mass that you have to have. Another big part of that is it's very easy to start a gas or diesel car, and if you've ever started a fire before with wood, you know that it takes a little bit of time. You have to get it going, and turning it back off, putting out a fire isn't just something where you can turn a switch and the fire goes out and you don't have to worry about it anymore. So then you might say, well, why don't we just use gas for everything? And the reason for that is because there's a lot of air pollution per joule of energy released. It might be the most efficient for transportation, but if you're able to run a power plant, for instance, on something like coal, because it does take a lot of energy to start up, you can keep that coal power plant running, say, nonstop. And that allows you to not have to worry about the startup cost. And then over time, you're going to get more energy with less pollution. And the other big part is gasoline does cost a lot of money. You have to process it. You have to refine it. You have to do a lot to it that you can't just, mine out the oil and take crude oil and turn it into gas. There's a lot more to it than that. So that'll bring us to 6.3 fuel types and uses. That'll be our next video. So make sure you check out 6.3. If you're curious, we did do all of these notes so far in class, but the video is available to help you out too.